In this video, we're going to look at aldehydes and ketones. Aldehydes and ketones contain the carbonyl group, and that carbonyl carbon behaves like an electrophile. Some aldehydes and ketones have distinctive flavors. Here are some aldehydes here, and here are some ketones there. I'm not sure how many of you go to the library since everything can be found online, but the smell of old books is due to chemicals, so stop the video and identify the aldehydes. So here are the aldehydes. Aldehydes and ketones are one of the functional groups found in carbohydrates. Here are some reactions that we have previously seen to prepare aldehydes and ketones. Note that these reactions are oxidation or reduction reactions. Next, we will look at how aldehydes and ketones react. So remember, we identified the structural features in the reactants, and based on those structural features, we can figure out what products form. Aldehydes and ketones undergo addition reactions. Let's see how a ketone reacts with a nucleophile and with an electrophile. So stop the video and use curved arrows to show how bonds break and form with a nucleophile and electrophile. With a nucleophile, here's what happens. The lone pairs on the oxygen behave like a nucleophile and react with the electrophile. Note that the product shows two resonance structures. Note that this resonance structure shows the carbonyl carbon being more electrophilic. A nucleophile reacts at the carbonyl carbon and forms a tetrahedral intermediate. We will see this tetrahedral intermediate in other reactions. We looked at alkene addition reactions earlier. Note that the alkene pi bond is a nucleophile and reacts with an electrophile. Aldehydes and ketones also undergo addition reactions, but the carbon and the carbonyl carbon is an electrophile and it reacts with a nucleophile first. So here are the two addition reactions. So this is an electrophilic addition reaction because the electrophile adds to the pi bond. And in this reaction, we have a nucleophilic addition reaction because the nucleophile reacts with the carbon to carbon. In the nucleophilic addition reaction, note that a tetrahedral intermediate forms. A nucleophile reacts at the carbonyl carbon and an aldehyde or ketone to form a tetrahedral intermediate. So in this video, we're going to look at the Grignard reaction and the cyanohydrin formation. In the next video, we're going to look at the nucleophile being either water or an alcohol to form an acetal. And in a future video, we'll look at the formation of imines and enamines with nitrogen nucleophiles. And when the nucleophile is the hydride ion, the reaction is a reduction of an aldehyde or ketone to an alcohol. The hydride comes from lithium aluminum hydride or sodium boryl hydride. The Grignard reaction is an important reaction because it makes a carbon-carbon bond to make a big molecule from a smaller molecule. So the Grignard reagent is made by reacting a alkyl halide with magnesium to form the Grignard reagent. So is the Grignard reagent a nucleophile or electrophile? Stop the video and think about that for a second. Remember that carbon-magnesium bond is a polar bond with the carbon having a partial negative charge and the magnesium having a partial positive charge due to electronegativity. So the Grignard reagent is a nucleophile. So the Grignard reagent reacts with an electrophile. One problem with the Grignard reaction is that everything has to be dry because water reacts with the Grignard reagent. So stop the video and use curved arrows to show how water reacts with the Grignard reagent. Here are two other compounds that react with the Grignard reagent. So stop the video and show how each substance reacts with the Grignard reagent. In the first reaction, here's what happens. This is a substitution reaction. This also means that an elimination reaction can also occur. In the second reaction, here's what happens. Remember that the Grignard reagent is a nucleophile and it either reacts at the alpha carbon in the substitution reaction or at the carbonyl carbon in the addition reaction. In lab 6, we're going to do this Grignard-like reaction. So rather than using magnesium to make the Grignard reagent, we're going to use zinc. The advantage of this reaction is we can do this reaction in water. So stop the video and draw the product of this reaction. Note that the tetrahedral intermediate forms here, and an alcohol is our product. Now, compare the Grignard reagent to this RZNX reagent. Which is the better nucleophile? So stop the video and think about that. Compare the difference in electronegativity of the carbon-magnesium bond to the carbon-zinc bond, and that'll tell you that the Grignard reagent is the better nucleophile. Another carbon nucleophile is the cyanide ion. When HCN reacts with an aldehyde or ketone, a cyanohydrin is produced. So stop the video and then use curved arrows to show the cyanohydrin is formed, and then you can answer this question. In the first step, here's what happens. Draw a resin structure of this intermediate. Note that the carbonyl carbon is now a better electrophile, and then the Cn- ion can react at the more electrophilic carbocation to form the cyanohydrin. A cyanohydrin, such as glyceronitrile, may stimulate seed germination and may help regrow a forest after fire. So let's work backwards and determine the reactants which would be used to make glyceronitrile. So stop the video and draw the reactants. And here's a hint. Which carbon came from the carbonyl carbon? So this carbon comes from the carbonyl carbon. And the reactants are, if you like tapioca, tapioca is made from cassava roots, but don't eat them raw because hydrogen cyanide gas is produced, which is very poisonous. So stop the video and determine what the other product of this reaction is. Note that here's the cyanide group, so it's not quite a cyanohydrin. So here's what happens. So remember to cook those cassava roots to avoid being poisoned with HCN.